Moving charges and magnetism. Introduction. Both electricity and magnetism have been known for more than 2,000 years. However, it was only about 200 years ago, in 1820, that it was realized that they were intimately related. During a lecture demonstration in the summer of 1820, Danish physicist Hans Christian Ørsted noticed that a current in a straight wire caused a noticeable deflection in a nearby magnetic compass needle. He investigated this phenomenon. He found that the alignment of the needle is tangential to an imaginary circle which has the straight wire as its center and has its plane perpendicular to the wire. This situation is depicted in the diagram. 4.1. It is noticeable when the current is large and the needle sufficiently close to the wire so that the Earth's magnetic field may be ignored. Reversing the direction of the current reverses the orientation of the needle. Figure 4.1b. The deflection increases on increasing the current or bringing the needle closer to the wire. Iron filings sprinkled around the wire arrange themselves in concentric circles with the wire as the center. Figure 4.1c. Ørsted concluded that moving charges or currents produced a magnetic field in the surrounding space. Following this, there was intense experimentation. In 1864, the laws obeyed by electricity and magnetism were unified and formulated by James Maxwell. James Maxwell, who then realized that light was electromagnetic waves. Radio waves were discovered by Hertz and produced by J.C. Bose and G. Marconi by the end of the 19th century. A remarkable scientific and technological progress took place in the 20th century. This was due to our increased understanding of electromagnetism and the invention of devices for production, amplification, transmission and detection of electromagnetic waves. In this chapter, we will see how magnetic field exerts forces on moving charged particles, like electrons, protons, and current-carrying wires. We shall also learn how currents produce magnetic fields. We shall see how particles can be accelerated to very high energies in a cyclotron. We shall study how currents and voltages are detected by a galvanometer. In this and subsequent chapter on magnetism, we adopt the following convention. A current or a field, electric or magnetic, emerging out of the plane of the paper is depicted by a dot. A current or a field going into the plane of the paper is depicted by a cross. Figures 4.1a and 4.1b correspond to these two situations, respectively. Magnetic force, sources and fields. Before we introduce the concept of a magnetic field B, we shall recapitulate what we have learnt in Chapter 1 about the electric field E. We have seen that the interaction between two charges can be considered in two stages. The charge Q, the source of the field, produces an electric field E, where R is unit vector along R and the field E is a vector field. A charge Q interacts with this field and experiences a force F given by the equation below. As pointed out in the Chapter 1, the field E is not just an artifact but has a physical role. It can convey energy and momentum and is not established instantaneously but takes finite time to propagate. The concept of a field was specially stressed by Faraday and was incorporated by Maxwell in his unification of electricity and magnetism. In addition to depending on each point in space, it can also vary with time, that is, be a function of time. In our discussions in this chapter, we will assume that the fields do not change with time. The field at a particular point can be due to one or more charges. If there are more charges, the fields add vectorially. You have already learnt in Chapter 1 that this is called the principle of superposition. Once the field is known, the force on a test charge is given by EQ. 4.2. Just as static charges produce an electric field, the currents or moving charges produce, in addition, a magnetic field, denoted by B, R, again a vector field. It has several basic properties identical to the electric field. It is defined at each point in space, and can in addition depend on time. Experimentally, it is found to obey the principle of superposition. The magnetic field of several sources is the vector addition of magnetic field of each individual source. Magnetic field, Lorentz force. Let us suppose that there is a point charge q, moving with a velocity v and, located at r at a given time t, in presence of both the electric field E, r, and the magnetic field B, r. The force on an electric charge q due to both of them can be written as. This force was given first by H. A. Lorentz based on the extensive experiments of Ampere and others. It is called the Lorentz force. You have already studied in detail the force due to the electric field. If we look at the interaction with the magnetic field, we find the following features. It depends on q, v and b, charge of the particle, the velocity and the magnetic field. Force on a negative charge is opposite to that on a positive charge. The magnetic force q, v times b, includes a vector product of velocity and magnetic field. The vector product makes the force due to magnetic field vanish, become zero, if velocity and magnetic field are parallel or anti-parallel. The force acts in a sideways direction perpendicular to both the velocity and the magnetic field. Its direction is given by the screw rule or right-hand rule for vector, or cross, product as illustrated in figure 4.2. E. The magnetic force is zero if charge is not moving, as then, versus, equals zero. Only a moving charge feels the magnetic force. The expression for the magnetic force helps us to define the unit of the magnetic field. If one takes q, F and versus all to be unity in the force equation, F equals q, V times B, equals qvB sin n, where is the angle between V and B, figure 4.2. The magnitude of magnetic field B is 1 SI unit, when the force acting on a unit charge, 1 C, moving perpendicular to B with a speed 1 meter per second, is 1 Newton. Dimensionally, we have B equals F qv, and the unit of B in Newton second, Coulomb meter. This unit is called Tesla, T, named after Nikola Tesla. Tesla is a rather large unit. A smaller unit, non-SI, called Gauss, equals 10⁻⁻⁴ Tesla, is also often used. The Earth's magnetic field is about 3.6 times 10⁻⁵ T magnetic force on a current-carrying conductor. We can extend the analysis for force due to magnetic field on a single moving charge to a straight rod carrying current. Consider a rod of a uniform cross-sectional area A and length L. We shall assume one kind of mobile carriers as in a conductor, here electrons. Let the number density of these mobile charge carriers in it be n. Then the total number of mobile charge carriers in it is nLA. For a steady current I in this conducting rod, we may assume that each mobile carrier has an average drift velocity Vd. In the presence of an external magnetic field B, the force on these carriers is, where Q is the value of the charge on a carrier. Now nqvd is the current density J and nqvd, A is the current I. Thus, where L is a vector of magnitude L, the length of the rod, and with a direction identical to the current I, note that the current I is not a vector. In the last step leading to equation 4.4, we have transferred the vector sign from J to L. Equation 4.4 holds for a straight rod. In this equation, B is the external magnetic field. It is not the field produced by the current carrying rod. If the wire has an arbitrary shape, we can calculate the Lorentz force on it by considering it as a collection of linear strips dl and summing. This summation can be converted to an integral in most cases. Motion in a magnetic field. We will now consider, in greater detail, the motion of a charge moving in a magnetic field. We have learnt in mechanics that a force on a particle does work if the force has a component along, or opposed to, the direction of motion of the particle. In the case of motion of a charge in a magnetic field, the magnetic force is perpendicular to the velocity of the particle. So no work is done and no change in the magnitude of the velocity is produced, though the direction of momentum may be changed. Notice that this is unlike the force due to an electric field, QE, which can have a component parallel or antiparallel to motion and thus can transfer energy in addition to momentum. We shall consider motion of a charged particle in a uniform magnetic field. First, consider the case of V perpendicular to B. The perpendicular force, QV times B, acts as a centripetal force and produces a circular motion perpendicular to the magnetic field. The particle will describe a circle if V and B are perpendicular to each other, figure 4.5. If velocity has a component along B, this component remains unchanged as the motion along the magnetic field will not be affected by the magnetic field. The motion in a plane perpendicular to B is as before a circular one, thereby producing a helical motion, figure 4.6. You have already learnt in earlier classes that if r is the radius of the circular path of a particle, then a force of mv square r acts perpendicular to the path towards the center of the circle, and is called the centripetal force. If the velocity v is perpendicular to the magnetic field B, the magnetic force is perpendicular to both v and B and acts like a centripetal force. It has a magnitude q versus b equating the two expressions for centripetal force. R is given by the equation R equals mv qb. For the radius of the circle described by the charged particle, the larger the momentum, the larger is the radius and bigger the circle described. If omega is the angular frequency, then v equals omega r. So, omega equals 2 pi nu equals qb m, which is independent of the velocity or energy. Here nu is the frequency of rotation. The independence of nu from energy has important application in the design of a cyclotron. The time taken for one revolution is t equals 2 pi, omega equals 1, nu. If there is a component of the velocity parallel to the magnetic field, it will make the particle move along the field and the path of the particle would be a helical one, figure 4.6. The distance moved along the magnetic field in one rotation is called pitch p. Using equation 4.6, we have the equation 4.6, b. The radius of the circular component of motion is called the radius of the helix. Magnetic field due to a current element, Biot-Savart law. All magnetic fields that we know are due to currents, or moving charges, and due to intrinsic magnetic moments of particles. Here, we shall study the relation between current and the magnetic field it produces. It is given by the Biot-Savart's law. Figure 4.7 shows a finite conductor XY carrying current I. Consider an infinitesimal element dl of the conductor. The magnetic field dB due to this element is to be determined at a point P which is at a distance r from it. Let be the angle between dl and the displacement vector r. According to Biot-Savart's law, the magnitude of the magnetic field dB is proportional to the current I, the element length, dl, and inversely proportional to the square of the distance r. Its direction is perpendicular to the plane containing dl and r. Thus, in vector notation, the magnitude of the magnetic field dB is given by equation 4.7 where mu naught, 4 pi is a constant of proportionality. The above expression holds when the medium is vacuum. The magnitude of this field is given by the equation 4.7b, where we have used the property of cross product. Equation 4.7 constitutes our basic equation for the magnetic field. The proportionality constant in SI units has the exact value. We call mu naught the permeability of free space, or vacuum. The Biot-Savart law for the magnetic field has certain similarities, as well as differences with the Coulomb's law for the electrostatic field. Some of these are both are long range, since both depend inversely on the square of distance from the source to the point of interest. The principle of superposition applies to both fields. In this connection, note that the magnetic field is linear in the source IDL just as the electrostatic field is linear in its source, the electric charge. The electrostatic field is produced by a scalar source, namely, the electric charge. The magnetic field is produced by a vector source IDL. The electrostatic field is along the displacement vector joining the source and the field point. The magnetic field is perpendicular to the plane containing the displacement vector r and the current element IDL. There is an angle dependence in the Biot-Savart law which is not present in the electrostatic case. In figure 4.7, the magnetic field at any point in the direction of dl, the dashed line, is 0. Along this line, theta equals 0, sin theta equals 0 and from equation 4.7, dB, equals 0. There is an interesting relation between epsilon naught, the permittivity of free space, mu, the permeability of free space, and c, the speed of light in vacuum, which is given by. Since the speed of light in vacuum is constant, the product mu0 and epsilon0 is fixed in magnitude. Choosing the value of either epsilon0 or mu0 fixes the value of the other. In SI units, mu0 is fixed to be equal to 4 pi times 10 power minus 7 in magnitude. In the next section, we shall use the Biot-Savart law to calculate the magnetic field due to a circular loop. 4.5 Magnetic field on the axis of a circular current loop. In this section, we shall evaluate the magnetic field due to a circular coil along its axis. The evaluation entails summing up the effect of infinitesimal current elements, IDL, mentioned in the previous section. We assume that the current I is steady and that the evaluation is carried out in free space, that is, vacuum. Figure 4.9 depicts a circular loop carrying a steady current I. The loop is placed in the YZ plane with its center at the origin O and has a radius r. The x-axis is the axis of the loop. We wish to calculate the magnetic field at the point P on this axis. Let x be the distance of P from the center O of the loop. Consider a conducting element dl of the loop. This is shown in figure 4.9. The magnitude dB of the magnetic field due to dl is given by the Biot-Savart law, equation 4.7 a. Now r square equals x square plus r square. Further, any element of the loop will be perpendicular to the displacement vector from the element to the axial point. For example, the element dl in figure 4.9 is in the plane, whereas the displacement vector r from dl to the axial point P is in the plane. Hence, dl times r equals r dl. Thus, dB is given by the equation 4.9. The direction of dB is shown in figure 4.9. It is perpendicular to the plane formed by dl and r. It has an x-component dbx and a component perpendicular to x-axis, dB. When the components perpendicular to the x-axis are summed over, they cancel out and we obtain a null result. For example, the dB component due to dl is cancelled by the contribution due to the diametrically opposite dl element, shown in figure 4.9. Thus, only the x-component survives. The net contribution along x direction can be obtained by integrating dbx equals dB cos theta over the loop. For figure 4.9, cos theta is given by. From equations 4.9 and 4.10, dB is given by. The summation of elements dl over the loop yields 2 pi r, the circumference of the loop. Thus, the magnetic field at P due to entire circular loop is given by the equation 4.11. As a special case of the above result, we may obtain the field at the center of the loop. Here x equals 0 and we obtain the equation 4.12. The magnetic field lines due to a circular wire form closed loops and are shown in figure 4.10. The direction of the magnetic field is given by another right-hand thumb rule stated below. Curl the palm of your right hand around the circular wire with the fingers pointing in the direction of the current. The right-hand thumb gives the direction of the magnetic field. Ampere's Circuital law. There is an alternative and appealing way in which the Biot-Savart law may be expressed. Ampere's Circuital law considers an open surface with a boundary, figure 4.12. The surface has current passing through it. We consider the boundary to be made up of a number of small line elements. Consider one such element of length dl. We take the value of the tangential component of the magnetic field, B, at this element and multiply it by the length of that element dl. All such products are added together. We consider the limit as the lengths of elements get smaller and their number gets larger. The sum then tends to an integral. Ampere's law states that this integral is equal to mu0 times the total current passing through the surface, that is, equation 4.13 where I is the total current through the surface. The integral is taken over the closed loop coinciding with the boundary C of the surface. The relation above involves a sign convention, given by the right-hand rule. Let the fingers of the right hand be curled in the sense the boundary is traversed in the loop integral of dl. Then the direction of the thumb gives the sense in which the current I is regarded as positive. For several applications, a much simplified version of equation 4.13 proves sufficient. We shall assume that, in such cases, it is possible to choose the loop, called an Amperian loop, such that at each point of the loop, either B is tangential to the loop and is a non-zero constant. B, or B is normal to the loop, or B vanishes. Now, let L be the length, part, of the loop for which B is tangential. Let I be the current enclosed by the loop. Then, EQ, 4.13, reduces to, when there is a system with a symmetry such as for a straight infinite current carrying wire in figure 4.13, the Ampere's law enables an easy evaluation of the magnetic field, much the same way Gauss' law helps in determination of the electric field. This is exhibited in the example 4.8 below. The boundary of the loop chosen is a circle and magnetic field is tangential to the circumference of the circle. The law gives, for the left-hand side of equation, 4.13, B2R. We find that the magnetic field at a distance r outside the wire is tangential and given by the equation 4.14. The above result for the infinite wire is interesting from several points of view. It implies that the field at every point on a circle of radius r, with the wire along the axis, is same in magnitude. In other words, the magnetic field